We've been talking about functions of two or more variables, and in previous videos we've defined concepts like limits or continuity of the function. Now remember that if you have a continuous function, its graph can't have any holes, gaps, jumps, or breaks. In a previous video we also discussed partial derivatives. Partial derivatives of a function were defined by holding one of the variables fixed and then allowing it to change with respect to the other variable. When you find the partial derivatives of a function, these produce new functions in general. Now, these new functions may or may not exist at every single point in R2, and they may or may not be continuous at all points in R2. What is the derivative of a multivariable function? And when is a multivariable function differentiable? If you've got a function of one variable, y equals f of x, remember that we introduced the derivative geometrically. So we will assume that f is differentiable at the point x equals a. So if you've got a differentiable function at that point, what it means is that it has a tangent line. And that tangent line we're going to call L of x. Now remember that the equation of a line in general is y minus y naught is m into x minus x naught. This point is the value of the function at a. We know that this is simply a, and the whole point of learning about calculus is you know that the slope is just given by f prime of a. So what this allows us to do is to reorganize the equation of this line for y. And this is what we call the linear approximation, or the tangent line approximation of the function at the point x equals a. It uses information about the function and its derivative at that point. Now remember, we assumed that the function was differentiable, which meant that f prime of a exists. Now here's an important point to note. The value of the linear approximation at a is just going to be the value of the function, so the two of them have the same height. Now there are infinitely many different lines that you can draw through that single point, but what makes this linear approximation special is that if you were to take its derivative, all you would get would be f prime of a. They have not only the same height, but they have the same slope at that point. If a function is differentiable at a certain point x equals a, that means it's locally linear. When you take it and you zoom in to a certain point, so again, if this is the tangent line, if we zoom into this point, what we're going to find that the closer we zoom in, the less and less we are going to notice the curviness of the function. So differentiable function is essentially linear at the point x equals a. That's what makes differentiable functions special. Now we're going to use this idea of local linearity to try to motivate how to extend differentiability to multivariable functions. So when we talk about a function, z is f of x and y, what we're trying to do is extend this local linearity property. The graph of this function is a surface in R3. Now, if a function is differentiable at this point, the surface should be locally linear at that point. And what that means is if you have the graph of some function and it's a surface in R3, when I select a certain point, I should be able to draw not a tangent line, but a tangent plane. And if we're interested in the point here, let's say a and b, that means that the function should have a tangent plane at the point a, b, and f of a, b. So the equation of a plane looked something like this. It was a into x minus x naught, b into y minus y naught, c into z minus z naught, and all of that was equal to 0. We know that the point we're interested in is a for the x coordinate, small b for the y coordinate, and then in the z coordinate, it's the value of the function at that point, and we want it to be equal to 0. What are the values of these three terms? Now, from an earlier video, we know that the vector that is normal to the plane had these three components. So this is the normal vector to the plane. And the normal vector was the vector that's perpendicular to the surface of that plane. The cross product will help me figure out what that normal vector is. So that means I need two vectors in the plane. And those two vectors are going to be u and v. So how do we find these two vectors in the plane? So we're going to revisit some ideas that we talked about last class. What we're going to do is intersect the surface with planes. And this is going to help us find two vectors that live in the plane. If I have this surface here, and I'm interested in this point right there, there's the tangent plane. I need to find one vector that lives in one direction and one that lives in the other direction. So we'll call this u and v, so that when I take their cross product, I will simply get the vector that's normal. Remember that we are living in a three-dimensional coordinate system. So if I intersect this with, let's say, y is equal to b. If I draw a picture of this, remember that y curves live here. So let's say this is the value of b. And so essentially I'm just going to be drawing in some plane that looks like this. And when that plane intersects the surface, there's going to be some curve of intersection. And this curve, remember, is z is a function of x only because we're taking the y value to be fixed. At the point we're interested in, this curve will go through the tangent plane. Here's the key observation. If I were to draw a tangent line right at that point, so I'm just going to take this picture and draw it over again. Now remember that there's an x, y, z coordinate system here. And if we're looking at this situation here, then essentially what we've got is a z and an x. The slope right at this point we talked about in a previous video when we introduced partial derivatives. So the slope of this tangent line is the partial derivative of the function with respect to x at the point a, b. If I were to go over 1 unit, then the height of this line would change by m. There's a vector that points in the direction of that line. So u is the vector that says if you move over 1 unit in the x direction, because you are in the plane y equals b, there's going to be no change in the y direction. And then the change in the z direction, the change in the height, is just given by the slope of that curve. So that's the value of the partial derivative at k. So what we have done is now found one of the vectors in the tangent plane. We're going to repeat this idea for the second vector. So now what we're going to do is intersect the function with the plane x equals a. So once again, we're going to take our function. There's an x, y, z coordinate system here. And if I were to intersect it with the plane x equals a, I'm cutting this surface, and there will be a different curve. Now remember, we're interested in some point on the curve, and there's a tangent line that occurs right at this point. So if I were to take this picture and draw it again, so this is the plane x equals a. In this plane x equals a, there's a curve. There's the point that I'm interested in. There's a tangent line. And then there's a vector that points in the direction of that tangent line. That vector is called v. I'm now going to superimpose this two-dimensional coordinate system. Remember that I'm holding x fixed at a value of a. If I were to move over 1 unit in this direction, the slope should tell me how high I go up. The curve here is the value of the function where x is fixed at a and it's a function of y. The slope of that function right at that point is the partial derivative with respect to y at the point a, b. And so the vector that points in the direction that I'm interested in, because I'm in a fixed x coordinate, there's no change in the x direction. If I change 1 unit in the y direction, I will now have to change this many units in the k direction. Now, it's really important to remember that in order for this to work, we have to assume that these partial derivatives exist at the point that we're talking about. If they don't exist, I won't be able to define those slopes, and then I won't be able to find those vectors. We've got our function. We've picked a point that we're interested in, and we're saying if the function is differentiable, we should be able to approximate it with this linear surface. At that point, there have to be two vectors that we found in the plane u and v, vectors that point in the direction of the tangent lines right there. And when I cross those vectors, I will get the vector n. Just from our definition of cross product, the vector u was 1, 0, partial derivative of x at the point. The other vector was 0, 1, partial derivative of y at the point. So just by doing a basic calculation, what you're going to find is negative partial derivative of x in the x direction, subtract a partial derivative of y in the y direction, and in that last component, all I will get is a 1. And the last thing that we need to do then is simply compute the equation of the tangent plane right at that point. The tangent plane at this point, AB, a into x minus a, capital B into y minus b, capital C into z minus the value of the function. At that point, it was equal to 0. Well, we've just figured out what a is. This is the value of a. This is the value of b. And this is the value of c. So the equation of this tangent plane becomes the x partial derivative with a negative into x minus a, the negative of the y partial derivative into y minus b, and then a plain old 1 into z minus this. So we've successfully computed the equation of the tangent plane, but what we're going to do is just rewrite this to try to mimic what was done in the single variable case. And if I rewrite it for z, what I'll get is z minus the value of the function at ab, subtract the partial derivative at ab times x minus a, subtract the partial derivative at ab with respect to y minus b. Now, all of this is equal to 0. So if I reorganize this for z, what I'll find is that this is going to be f of ab plus the x partial at ab, x minus a plus the y partial at ab, y minus b. Now, I've left a gap in there because I'm going to give this a new notation. I'm going to call this L of x and y, the linear approximation of our function f at the point a, b. Now, just like before, when I'm actually at the point a, b, the value of the linear approximation is equal to the value of the function, but there are infinitely many different planes that will do that. The x partial derivative is simply just going to be equal to the x partial derivative at that point, and then the y partial derivative of the tangent plane is just equal to the y partial derivative here. So what we've done is come up with the equation of a linearized version of my function. Remember, I'm assuming that my function can be zoomed into and stay locally linear. So just as an example, let's find the equation of the tangent plane to this function. Z is 9x squared plus y squared plus 6x minus 3y plus 5 at the point 1, 2, and 18. This function is the function of two variables, and this value means that when I plug in 1, 2 into this, I should get an 18. So the equation of the tangent plane is going to require partial derivatives. So the partial derivative function here is an 18x plus 6, whereas the partial derivative with respect to y is going to give me a 2y minus 3. Both of these functions exist at the point that I'm interested in. If I were to plug in a 1 and a 2, I'll get 18 plus 6, which is a 24. And if I were to plug in a 1 and a 2 into this function, I will get a 2 times 2 minus 3, which is a 1. So both of them exist at the point 1, 2. Now also note, this is a linear function. So this function is continuous for all points in R2. And the same thing is true here. This partial derivative function is continuous for all points in R2. So the question said, find the equation of the tangent plane, the value of the x derivative, x minus 1, plus the value of the y derivative, y minus 2, plus the value of 1, z minus 18 is 0. So if I were to reorganize this, I'll get z is 18 plus 24 into x minus 1 and 1 into y minus 2. So this thing right here is the linear approximation of the function. Now we can use this to approximate the value of the function at some nearby point. So if I said, hey, let's approximate the value of this function at 1.1 and 1.9, well, the whole point of a differentiable function is that you could replace it with the value of the linear approximator. So this would then be 18 plus 24 into 1.1 minus 1, 1 into 1.9 minus 2. So I'll get 18 plus 24 into 0.1 plus negative 0.1. So at the end of the day, I'll get 18 plus 2.4 minus 0.1, which is going to give me 20.3.